My name is Maggie Fowler, and today I'll be talking about Lab 5. So in this lab, we dropped a bar magnet down an aluminum foil tube, and we used Faraday's law to relate the magnetic field changing in time due to the falling bar magnet to the Curly E field it produced, which induced a current in the aluminum foil tube. And then this current in the aluminum foil tube produced its own magnetic field, which exerted a magnetic force on the falling bar magnet, slowing it down. And then we compared our observed data to the computational glow script model. So the reason we couldn't use a ferrous tube is because ferrous metals are magnetic, so they'll create their own magnetic field, which would interfere with the magnetic field due to the bar magnet and would mess up our data. So the physics principles used in this lab were Faraday's law, Newton's laws, and the Biot-Savart law. So Faraday's law relates the Curly E field to the change in flux, and that's what's right here. And then we use Newton's second law, which is force equals mass times acceleration, and then Newton's third law, which is about how when two objects exert a force on one another, they are equal in magnitude and opposite in direction. And then we use the Biot-Savart law, which is also right here. So the falling magnet, when it goes through the tube, it goes slower than it would fall in free space. And then the average time I calculated for the magnet to go through the tube was 1.232 seconds. And the magnetic moment I used was from lab 3, which was mu equals 2.0963. And then the aluminum foil tube I used was 12 inches long, and the diameter was 3.5 centimeters, and the thickness of the foil was 0.4 centimeters. And then here's just a video of me dropping the magnet down the tube. So I can put that again. All right, so the first thing we did for the coding was set up our initial conditions. So up here I have the geometry of my tube, and down here I have the magnetic moment of my bar magnet. And then we had to create a function calculating the magnetic field at a position relative to the bar magnet, and we just used our function from lab 3. And then down here we had to calculate the rate of change in the magnetic flux through each ring caused by the falling magnet. And then here it was essentially just the equation from the edX video. And then we had to use Faraday's law to calculate the current induced in each ring by the falling magnet. So that's just the change in flux over the resistance. And then we had to calculate the force exerted on each current carrying ring by the falling magnet, and then calculate the force exerted on the falling magnet by the whole tube of current carrying rings. So first we calculated the current, like the force exerted on each current carrying ring, and then we know that from Newton's third law, the magnitude of the force exerted on each ring, if you add them all up, that should be the magnitude of the force on the magnet. And then we calculated the net force on the magnet, which is just the force due to gravity and the force due to the entire aluminum tube. And then we used Newton's second law, force equals mass times acceleration, to write our position and velocity updating codes to model the motion of the falling magnet. So that's just the bar.bell and the bar.pause down here. And then for a computational model, for my model, I had red above the magnet and blue below the magnet. And then from here, you could just use Lenz's law, where you put your thumb in the direction of negative dB dt, and your fingers curl in the direction of the Curly E field. So we know that red is clockwise and blue is counterclockwise, just by using like Lenz's law. And then if you flip the magnet around, you could just use Lenz's law again. So I just did this on paper, but essentially the red and the blue rings just switch. So for our computational model, we calculated that the falling magnet should be in the tube for 1.809 seconds, and then the real world, I calculated 1.232 seconds. And the difference here is just due to human error and then environmental factors, like there being other electronics around. And then of course my mu from lab 3 could have been incorrect. And then the shape of the velocity versus time plot. So you'll see here, when the velocity is constant, that means the net force acting on the magnet is 0 because there's no acceleration. So you know that the magnitude of the force due to the aluminum foil tube is equal to the magnitude of the force due to gravity. And then of course, when the velocity is not constant, that's because the only force acting on the magnet is the force due to gravity. So our final questions, if the resistivity of the conductor was reduced to close to 0, then the induced current in the aluminum foil tube would be larger, so the magnetic force from the tube acting on the falling magnet would be larger, so the magnet would fall slower. And then if there were holes or slots cut in the tube, the induced current in the aluminum foil tube would be weaker, so this would have the opposite effect. So the magnetic force acting on the falling magnet would be weaker, so the magnet would fall faster. Thanks.